homologous series to which compound B belongs to. So let's go to our compound B and see what is happening. It will be easy to see that compound B is an ester because of this functional group that we have here. Compound B is an ester. So the answer to 2.1.1, that compound B is an ester. And then the second question, 2.1.2, we're looking for the IUPAC name of the same compound. So this is how you actually name an ester, ladies and gentlemen. You're going to come here to the structure and you're going to put a line that divides the oxygen with the double bond from the oxygen with the single bond. And then the part of the structure that has the oxygen with the single bond is coming from the alcohol. And the part of the structure that has the oxygen with a double bond is coming from the acid, because we know that in order to form an ester you need an alcohol and an acid in the presence of H2SO4. So let's look at our alcohol. Our alcohol that was used in making this ester is methanol. Why are we saying it is methanol? Because of this single carbon right here. And the acid that was used to make this ester is propanoic acid. Why are we saying so? These three carbons that we have there. So when we name this ester, the name is going to be methyl propanoid. Methyl propanoid. Right. So this methyl here is coming from the fact that the alcohol that was used is methanol. If the alcohol that was used was butanol, then the name would start by saying butyl. And then the propanoid is coming from the acid that was used, propanoic acid. Let's move to the second question, 2.2 and 2.2.1. An alcohol and an acid are heated in the presence of concentrated sulfuric acid to form compound B. Write down the role of the concentrated sulfuric acid in this reaction. So sulfuric acid in an esterification acts as a catalyst. So the answer to 2.2.1 is catalyst. It acts as a catalyst. It speeds up the reaction. You can also say that. And then the answer to 2.2.2, names of the alcohol and the organic acid used to prepare compound B. So we have already deduced which alcohol was used and which acid was used when we were naming our compound B, right? So now we're just gonna say the alcohol that was used is methanol and the acid that was used is propanoic acid. The acid that was used is propanoic acid. 2.2.3, name of the type of reaction that is taking place. Obviously the name of the reaction that is taking place is esterification. And other books will say condensation, which is also correct. I see that option time after time in memos. That is 2.2. Let's move to 2.3. So in 2.3, from the table above, consider compound C. So let's go to compound C and see what I have. Compound C, we have an acid. This is the functional group of an acid. Ethanoic acid to be specific. Let's go to the questions. 2.3.1. So the first question, 2.3.1, write down the name of the functional group of compound C. So we've already deduced that compound C is an acid, right? The name of the functional group of acids is carboxyl. So we have carboxyl group. That is the name of the functional group. And then 2.3.2, to which homologous group does compound C belong to? It is a carboxylic acid. That's an easy question to answer. It is a carboxylic acid. 2.3.3, differentiate between the terms functional group and homologous series. This question is actually just asking you to define homologous series and functional group. So let me just remind you, homologous series is a series of organic compounds that can be described by the same general formula. a series of organic compounds that can be described by the same general formula. While functional group, on the other hand, is a bond or an atom or a group of atoms that determines the physical and chemical properties of a group of organic compounds. There we go. You just need to define functional group and homologous series for 2.3.3. 2.4 for the table above, from the table above, actually, consider compounds A, D, and F. And then the first question, write down the homologous series to which they belong to. So let's go to compound A. Compound A, we have an OH, which is the functional group of an alcohol. So we know that compound A is an alcohol. And then compound D, we also have another OH, so that is another alcohol. Let's look at compound F. It ends with ol, so we have another alcohol again. So A, D, and F are alcohols as far as the homologous series is concerned. So the answer to 2.4.1 will be alcohols, because A, D, and F are all alcohols. 2.4.2, compound A and D are isomers. As what type of isomer will they be classified? So let's go to A and D. A and D. So A, let me just write down A real quick for the sake of clarity. So for A, we have something like this. We have hydrogens everywhere else. And then let's look at D. So for D, we have condensed structural formula, which we're gonna write in full now. So we have a carbon with 3 hydrogens. We have the second carbon, and then on the second carbon we have 1 hydrogen and an OH, and then the third carbon with 3 hydrogens. So what type of isomers is compound A and D, not B? Excuse me, compound A and D. So compound A, the OH is on the first carbon, and then for compound D, the OH is on the second carbon. So they have the same molecular formula, but just different position of the functional group. So those are called positional isomers. So 2.4.2, the answer here is positional isomers. They will be known or referred to as positional isomers, compound A and D. The third question, 2.4.3, we asked to draw the structure of compound F. Let's go ahead and look at compound F. So for compound F, 2-methyl propane 2-ol. So let's start with the prop. So as soon as we see prop, we know that we need 3 carbons. So we have 1, 2, 3, and then 2-ol. This 2-ol tells us that the OH is on the second carbon. So let's have that OH right here. And then this 2-methyl, we have a branch on the second carbon. So we're gonna have 1 carbon there, and then now we just left out with the hydrogens, and we have the structural formula of compound F just like that. Let's go ahead and move to 2.5. So 2.5, we're interested in compound G and compound E. 2.5.1, we're supposed to name compound G. Let's go to compound G. So compound G, the first thing that we must look for is the longest carbon chain. It is easy to see that this will indeed be our longest carbon chain. Let's count that. 1, 2, 3, 4, 5, 6. That is hex. And then as soon as I see Br, I know that it is a haloalkane, right? So it will be hexane. Now I'm just left with the branches. Where do I start numbering? If you start numbering from the left, on the second carbon, you have Br, you have bromo. And then if you start numbering from the right, on the second carbon, you have methyl, you have dimethyl, right? So the question now is, what takes preference between a branch and a halogen? Well, according to the exam guideline, nothing takes preference between the halogen and the branch. You just have to start numbering from the side that will lead to the smallest number. What do I mean by that? If we start numbering from the left, then we're going to have 2 for brom, right? And then this is 2, 3, 4, 5. And then we're going to have 5, 5 for that dimethyl. And then these numbers will give us 12. If we start numbering from the right, we're going to have 2.2 for the dimethyl, right? And then we're going to have 5 for the bromo. So this is 2 plus 5, which is equals to 9. If we start numbering from the right, we have the smallest number, and that's what we need to do. Nothing is going to take preference between the halogen and the branch. So we're going to have 5 bromo. We're going to have 5 bromo dash 2.2 dash dimethylhexane. 2.2 dash dimethylhexane. And that is the name of our compound G. The last question, structural formula of compound E. Let's go ahead and look at compound E. So compound E, we have 2.4 dimethyl pent 1-ene. So pent 5 carbons, 1, 2, 3, 4, 5. And then we have a double bond on the first carbon. We can tell from this pent 1-ene. So there we go, we have a double bond. And then on the second carbon, we have a branch with 1 carbon. And then on the fourth carbon, we also have another branch with 1 carbon. So now we're essentially done. We just left with filling out the hydrogens. So let's go ahead and do that. Yeah. So 1, 2, 3, we still need another hydrogen. And then 1, 2, 3. It's a painful exercise, but yeah, we have to do what we have to do. Compound A and B are functional isomers, like we are told in 3.1.1. What we are actually required to do is define the term functional isomer. Like all isomers, we have the same molecular formula, but in this case, the compounds differ by functional group. So the definition for functional isomer, same molecular formula, but different functional groups. Let's look at 3.1.2. Write down the IUPAC name of compound B. So the first thing you want to do is to determine which homologous series this compound B belongs to. Because of the structure of the functional group, compound B, it's a ketone. This carbon that is bonded to the oxygen is bonded to 2 other carbons. And because of that, we can conclude and say that compound B is a ketone. Now what we need is the longest carbon chain. Clearly, it is easy to see that this will be our longest carbon chain with 1, 2, 3, 4, 5 with 5 carbons. So we know we have pentane. We have pentane. Now what we need, or what we're looking for, is the position of the carbon that is bonded to the oxygen. If we start numbering from the left, we're going to have 1, 2, 3. If we start numbering from the right, we're going to have 1, 2, 3. So where we start numbering really doesn't matter. Our functional group is on the 3rd carbon. So we're going to have pentane 3-one. That is the answer to 3.1.2. Let's look at 3.1.3. How does the boiling point of A compare to that of pentane 1-ol? So we have pentane 1-ol and compound A. Write down only greater than, equal to, or lower than. So let's go to compound A. Compound A is an aldehyde because the carbon that is bonded to the oxygen is only bonded to 1 other carbon. So that makes it an aldehyde. So we have pentane 1-ol and pentanol. Pentane 1-ol is an alcohol. So it consists of hydrogen bonding. We have hydrogen bonding in alcohols. And then pentanal is an aldehyde. It consists of dipole. So the intermolecular forces in pentanal is dipole. So in order to answer this question, you actually need to know which intermolecular force is generally stronger between hydrogen bonding and dipole. Compound A will have a lower than boiling point compared to pentane 1-ol. Let me explain why that is the case in 3.1.4. The intermolecular forces in pentane 1-ol, which happens to be hydrogen bonding, are stronger than the intermolecular forces in pentanal, which is dipole. And then you know that if you have stronger intermolecular forces, then more energy is required to overcome those intermolecular forces in that compound. And then as a consequence, the alcohol or pent1-ol will have a higher boiling point. That is the answer to 3.1.4. Let's look at 3.1.5. How will the vapor pressure of compound B compare to that of pentane 1-ol? That only higher than, lower than, or equal to. Explain the answer fully. So compound B, like we've already deduced, is a ketone. And which intermolecular forces do we find in ketones? We have dipole forces. And then again in pentane 1-ol we have hydrogen bonding. In pentane 1-ol we have hydrogen bonding. So that will lead to ketone having a higher than vapor pressure compared to pentane 1-ol. Higher than vapor pressure. So what you have to understand is that the weaker the intermolecular forces, then the higher the vapor pressure. So between compound B, our ketone, and pentane 1-ol, pentane 1-ol has stronger intermolecular forces. So it will require more energy to overcome the intermolecular forces. And then as a consequence, it is going to have a lower vapor pressure. It is going to have a lower vapor pressure compared to ketone. Ketone will actually have a higher vapor pressure. So what you need to memorize, or what you need to know, is that the stronger the intermolecular forces, the higher the boiling point, the higher the melting point, but the lower the vapor pressure. You need to know that. 3.2.1. Let's define the term boiling point. That is not the temperature at which liquid turns to gas. Please, we no longer use that definition at this level. It is actually the temperature at which the vapor pressure equals the atmospheric pressure. The temperature at which the vapor pressure equals the atmospheric pressure. That is boiling point. 3.2.2. Write down the independent variable for this investigation. Let's take a look at what is happening in this question. Let us use compound C to E to investigate one factor which influences the boiling points of organic compounds. What I'm realizing real quick is that in compound C we have 1, 2, 3, 4. We have 4 carbons, right? And then in compound D we have 1, 2, 3, 4, 5. We have 5 carbons in compound D. And then in compound E we have 1, 2, 3, 4, 5, 6. We have 6 carbons in compound E. So it seems like our independent variable here, what we are changing, is actually the chain length. We can see that from the number of carbons we have in the compounds. So the answer to 3.2.2 would be chain length, or the molecular mass, because as the chain length increases, then the molecular mass is also going to increase. So that is the independent variable. And 3.2.3, write down the type of van der Waals force that occurs between these organic compounds. So these organic compounds are all alkenes, right? Well, you can draw compound C fairly quick by saying C, 1, 2, 3 hydrogens, and then another carbon with 2 hydrogens, another carbon with 2 hydrogens, and the last carbon with 3 hydrogens. The same thing with compound D and E, they're all alkenes. So the force that is occurring in compound C, D, and E is actually London force. That is London force, or induced dipole forces. Well, let's look at 3.2.4. Write down the conclusion that can be drawn about the boiling point of straight chain alkenes. So let's look at our diagram. We can see fully well that as the number of carbon is increasing, our boiling point is increasing from -1 to 36.1 and lastly to 69. So we can conclude and say that as the chain length increases, the boiling point increases. If you had said molecular mass in 3.2.2, you would say that as the molecular mass increases, the boiling point increases. How can we boil down these complex concepts to a few bullet points? Well, if a reaction starts with an alkene and you get whatever product you're going to get, then that reaction is an addition reaction. If a reaction starts with whatsoever it is starting with and it ends up with an alkene, then that reaction is an elimination reaction. And if our first condition is not met and our second condition is not met, then that reaction is a substitution reaction. What am I even saying? Let me show you what I'm talking about by answering this question. Let's look at 4.1. Consider reaction A and write down the type of reaction that takes place. So reaction A is right here. So let me go through my conditions and see which one is met. Do we start with an alkene? No, we don't. We start with a secondary alcohol. Do we end up with an alkene? Yes, we do. We have propene as our product, right? So we know fully well that from that only, our reaction is an elimination reaction. Our second condition is met. So the answer to 4.1 is elimination. It's elimination. Just because we know that if a reaction ends with an alkene, it's elimination. If it starts with alkene, it's addition. And then if none of that is correct, then it is a substitution reaction. Let's do 4.2 and 4.2.1. Reaction B represents a hydration reaction. Let's look at B. At B, we're starting with propene and we end up with a secondary alcohol. And then we are told that that reaction is a hydration reaction. Right, and then now what we're asked to do is to define hydration reaction. It is the addition of water to a compound. That's it. That's the definition. It's the addition of water to a compound. That's what we mean when we talk about a hydration reaction. We add in H2O to a compound. And the follow-up question, 4.2.2, write down the name or formula of the catalyst used for this reaction. So a catalyst you can use for a hydration reaction is H2SO4. So we can use sulfuric acid as a catalyst for a hydration reaction. Let's look at 4.3 and 4.3.1. During reaction C, a specific rule is followed to determine the major product when HBr is added. Let's look at reaction C. So for reaction C, we're starting with propene and we end up with 2-bromopropene. So let's go back to our conditions. Do we start with an alkene? Yes, we do. So we know that reaction C is supposed to be an addition reaction. Well, the answer to 4.3.1 was actually very difficult to find. But if you visit the CAPS document and other relevant resources, you'll find out that for hydrohalogenation, our addition reaction in this case, we need no water because alkenes cannot react with pure water. And then apart from needing no water, we need a concentrated strong acid. So we need a concentrated strong acid for this reaction that we have in 4.3.1. It is an addition reaction, namely hydrohalogenation. We're adding a hydrogen and a halogen. 4.3.2, use structural formula and write down the balance equation for this reaction. So propene plus HBr. Let's go ahead and do that. So we're going to have 1, 2, 3 carbons, right? So 1, 2. Now we just need to add our hydrogens, and we're supposed to have something like that, plus HBr to give us something. If you look back to the equation statement, it says that During reaction C, a specific rule is followed to determine the major product when HBr is added. So now you actually have to know that rule in order to answer this question. Well, to some extent, we know that this double bond is going to break, and either one between H and Br is going to come to the second carbon, and then the other is going to come to the first carbon. So do we get Br on the second carbon, or do we get Br on the first carbon? You need to know where to place that Br, because if you place it at the wrong location, then you lose a mark. But there's a rule for that. There's a law for that. Markovnikov's rule. So basically what it is saying is that the hydrogen is going to go where there's a lot of hydrogens, and then the halogen is going to go to the other spot. So if you look at this carbon here, it has 2 hydrogens, and then the carbon in the middle has 1 hydrogen. So the hydrogen will tend to go to the carbon with a lot of hydrogens already. So that Br, it will usually go to the middle, because that's where we have the least number of hydrogen. So our product is gonna look like this. Br is gonna come to the carbon in the middle, and the hydrogen is gonna come to the first carbon. And then now it's just a matter of filling out our hydrogens. So this is our major product according to Markovnikov's rule. And then Br being on the first carbon and H being on the second carbon is our minor product. This is our major product. Yeah, usually when this reaction occurs, this is the product. Right. 4.1. Identify the type of reaction taking place at, so let's go to reaction D. Reaction D. Yeah, this one is going to be easy because we know our conditions. Do we start with an alkene? No. Do we end with an alkene? No. So we know that it is substitution. It is substitution. There isn't a lot to think about there. And then 4.2. Which reaction are we interested in? We are interested in reaction F. In reaction F, do we start with an alkene? The answer is no. Do we end with an alkene? The answer is still no. So again, that is a substitution reaction. That is a substitution reaction. It cannot be otherwise. And then 4.5.1. Reaction E is a hydrogenation reaction. Let's look at reaction E real quick. We're starting with propene and we're ending up with propane. So it is indeed a hydrogenation, right? And then what does the equation say? Write down the 2 reaction conditions for this reaction. 2 reaction conditions for hydrogenation. So we need heat, and another thing we need is a catalyst. We need a catalyst. Yeah, which catalyst in this case? We need palladium, platinum, nickel, and so on. Right. And then 4.5.2. Name one use of hydrogenation in the food industry. Well, I will leave that one to you.